Good day, students. Welcome to mathgotserved.com. In this clip, we're going to be going over how to graph transformed trig functions. Alright, the instructions for the example are for us to graph one period to the left and right of the phase shift of the given function. Okay, so let's say for number one we have the function f of x equals negative 2 sine 2 pi x minus 4 pi. That quantity plus 1. Okay, so let's get started. In order to generate the graph of this function, one period to the left and right of the phase shift, we are going to have to find the properties of this transformed trigonometric function. Okay, so in order to determine the properties, we need to use A, B, C, and D. So to do that, we're going to write the general form for a transformed trig function. We'll place that underneath here. So we have f of x equals a sine bx plus c plus d. Okay, so with this form right here, we can easily identify what a, b, c, and d are. Alright, so let's go ahead and write them down. A is negative 2, b is 2 pi, c is negative 4 pi, and d is 1. Okay, so let's go ahead and write down the properties of this trig function that we have here. The properties are as follows. Let's start with the period. The period is given by the formula 2 pi. In most textbooks you see 2 pi over b, but to be more specific is 2 pi over the absolute value of b, because a period can never be negative. Okay, so 2 pi over b, or pi over the absolute value of b for tan and cotangent functions. So if you have tan and cotangent functions, your period will be, you use pi over the absolute value of b to compute those periods. Okay, but for sine, cosine, secant, and cosecant, 2 pi over the absolute value of b will suffice. Now let's apply this formula to this situation here. We have 2 pi over the absolute value of b, absolute value of 2 pi, and then when you divide that, you end up with 1. Okay, so what does this tell us? It tells us that when we are calibrating our x-axis, this is going to be you're going to have 4 ticks for the function you're graphing. We're graphing the negative sine function, so let's draw what it looks like. The negative sine function looks like an s that has been flipped across the x-axis, has been reflected about the x-axis. So 4 ticks for your reflected sine function is going to be 1 unit wide. Okay, that is the length of the period. So keep that in mind. Next thing we want to find is the frequency. Okay, the frequency is simply the reciprocal of the period. So the frequency is going to be absolute value of b over 2 pi for your sine, cosine, secant, and cosecant functions, or the absolute value of b over pi for tan and cotangent. Okay, tan and cotangent. Okay, so in this case, all we're just going to do is reciprocate the answer that we got, which is 1. So if you reciprocate 1, you're going to get 1. So graphically, you don't really see the frequency. The frequency just represents cycles per unit time. All right, so we have that down. Next thing is the amplitude of our function. So the amplitude is given by the formula absolute value of a. And you want to know that you want to know the direction of the amplitude. The amplitude goes up and down. All right, is the displacement to the max and min from the central position. Okay, in this problem, the absolute value of a is going to be the absolute value of -2. Remember what absolute value is. It is the distance of a number from 0 on the number line, right? So the absolute value of -2 is just 2 because 2 is 2 units from -2 on the number line. Alright, so what does this number signify on the graph? This number tells you that you're going to go 2 units to the max and min from the center. Okay, so from the center, you're going to go 2 units from center to the max and min of the trig function. So those would be your boundary values. All right, now let's take a look at the shifts. Let's start with the phase shift. The phase shift is given by the formula -c/b. Now, the phase shift is just another fancy word for horizontal shift. Okay, so just keep in mind that the phase shift is going left and right. That's how the phase shift affects the graph. All right, so -c/b, we'll look at that value and it tells us which shift to the left or right we're going to be making from the original origin. All right, in this problem, -c/b is going to be given by negative minus -4 pi. So c is negative, so you want to be careful about that, divided by b, which is 2 pi. Now when you multiply the minuses, minus times minus is a plus. You have 4 pi over 2 pi. And when you divide it, the pi's cancel out. 2 goes into 4 twice. So that's your phase shift. Alrighty? So your phase shift tells us what on the graph? On the graph, the phase shift tells you that your new y-axis is going to be 2 units to the right. Okay, so your new y-axis is 2 units to the right of the original. Okay. All right, so we have our phase shift down. That's our shift left or right. How do we determine the shifts up or down? That movement up or down is known as vertical movement. So let's figure out what our vertical shift is. Our vertical shift is given by the d value. Okay, so the d value tells us what the vertical shift is, and in this problem, the d value is what? What's the d value? The d value is 1. Graphically, what does that mean? Having a vertical shift of 1 just tells us that the new x-axis is going to be shifted 1 unit, where 1 unit upwards from the original x-axis. Okay? Alright. Last thing we need is a new origin. Where's the new origin going to be? The new origin can just be determined by combining the phase shift and the vertical shift. The x-coordinate of the new origin is simply your phase shift, which is -c/b, and the y-coordinate is d. Okay, so there goes your new origin right there. So let's write it down. Our new origin is negative c over b. We got 2 is 2 comma our d value is 1. So there you have it. Now to help us set up the graph to ensure that we don't draw our graph outside the paper, let's go ahead and set up a window to know what boundaries we want to keep our graph within. Okay, so we're going to set up a window. Um, so let's start with the center or new origin. The new origin is 2, 1. So from the new origin, we're going to go up and down by the amplitude. Okay, so we're going to go a certain amount of units up and a certain amount of units down. Okay, so we're going to use the amplitude here. So let's go ahead and do it. What is the amplitude? The amplitude is 2. So we're going to, starting from the y-axis, we're going to add 2 to get to the maximum. So either plus 2 to get to the max, or we subtract 2 to get to the min. Okay? So let's determine what the values are. Remember, the amplitude values apply just to the y-coordinate. So 1 plus 2 will take us to 3, and that's going to be a maximum on the graph. Okay? And then 1 minus 2 is negative 1, and that's going to be the minimum on the graph. The question asks us to graph one period to the left and one period to the right of the phase shift. So we have the phase shift here. So we're going to graph one period to the right and one period to the left. It's just a specification of the problem. Okay, so let's see. From the center, if we apply this direction, we're going to have we're going to add the length of one period to the x-coordinate. So period is 1 unit long, so plus 1. And we're going to subtract the length of one period from the x-coordinates to know the left boundary for our graph. Okay, so these values are our periods. So this is a period added, and then this is a period subtracted. Alright, and then these values that we are going up or down, that's the amplitude. So that's the amplitude, and that's the amplitude. Okay, so if you add 1 to 2, you're going to end up with 3. And then if you subtract 1 from 2, you end up with 1. Alright, so these are the boundaries of our graph. It goes as high as 3, to the right 3, down negative 1, and to the left negative 1. Okay, so let's go ahead and draw the graph. You notice that our center is in the first quadrant, and we go to this dip into the fourth quadrant just by 1 unit, and everything else stays in the first quadrant. So we don't care about quadrants 2 and 3 in this graph. Alright, so let's go ahead and shift our x-axis down because we just have 1 unit in the fourth quadrant. Okay, let's go ahead and calibrate our axis. So when we're calibrating our axis, you want to pay attention to the multiples of your y's and x's. Okay, so for the calibration of the y-axis, we're looking at this number, and that number. They are all constants. They're all numbers. Okay, had it been that they're multiples of pi, as you will see in some problems, that will mean that your calibration here should reflect that multiple of pi. So they're just numbers here, so they'll just be numbers here. Alright, so let's go ahead and put them down. So this right here is going to be negative 1, our minimum, 0, and then this is 1, and then this is 2, and then this is 3. Stop right there. That's the maximum. It's good enough. Alright, let's calibrate the x-axis. Now the calibration of the x-axis is a little bit more technical. Okay, for the x-axis, we're going to follow the instructions that we determined earlier with the period. 4 ticks for the period is going to be 1 unit wide. So we've got to keep that in mind. So let's go ahead and apply that here. So 4 ticks, 1, 2, 3, 4. So the 4 ticks, you can think about your 4 quadrants representing a complete cycle. So each tick is like a quadrant, and then that's a period, which is a complete revolution for your sine, cosine, and your reciprocals. Alright? So we're going as far as 3. So that's not good enough. We're going to keep going. 1, 2, 3, and then that's 2. Keep on going. 1, 2, 3, and then bam. That's how far we go. Alright, so you see the beauty of having the window. It helps you know exactly how far to go in each direction, so you're not just blindly um, calibrating your axis without knowing how far to go. Alright, so we have it nicely set up. First thing we're going to draw is the new origin. The new origin is centered at 2, 1 right here. So this can help me graph my new x and y axis, because we determined those from the phase shift and vertical shift. Okay, let's go ahead and graph those. We're gonna make them red. So let's draw the new y-axis first. So there goes your new y-axis, and then your new x-axis. There goes your new x-axis right there. Okay, so let's go. Let's label them. Make sure it's nicely centered. Okay, that's good. All right, let's go ahead and label them. What we just sketched on the graph. This is our new y-axis. New y-axis, and this is our new x-axis. So when we're drawing our transformed trig function, we are not going to pay any attention to this anymore. It's relative to this new coordinate system that we just created. Okay, alright, so we want to draw our max and min. So we know it's just 2 units up and down from the central position. So let's go ahead and graph those. Let's make it blue. So our maximum is 3. And then the minimum is, it drops down to -1. So our minimum is -1. Right there. Okay, so you see the symmetry here. If you draw it correctly, you should see the symmetry between the distance from the new x-axis to the max and to the min. So let's label them. This is our maximum displacement, max, and this is the min. Alright, so we're going to be drawing our negative sine function in here. So hopefully you remember the orientation of your trig functions. If you do not, let's refresh our memory real quick. So just remember that sine is like an S, okay? So sine is like an S. Alright, that's one period. Negative sine is like this S, but it's reflected vertically. So something like that. It's like this, but in the reverse direction. Cosine is like a cup. Okay, so your cosine function is like a cup. And then your negative cosine function is like a cup that has been flipped upside down. Alright, so just something like that. So these are just a period of the sine, negative sine, cosine, and negative cosine. The one we are drawing is this one right here, negative sine. So let's go ahead and put in the points to guide the construction of the curve. So the origin, you go 1 tick mark takes you to the minimum. 1 tick mark takes you back to the center. 1 tick mark takes you to the maximum. 1 tick mark takes you back to the center. This is one complete period of the negative sine function. So we need one period to the right of the phase shift and then one period to the left. So we're going to go 1 tick mark to the maximum, 1 tick mark back to the center, 1 tick mark to the minimum, and 1 tick mark back to the center. Alright? So these are the points for your sine negative sine function. Let's go ahead and connect the dots. So beneath is concave up, and then concave up to the center, and then concave down to the max, and then concave down and straight to the center, concave down and straight to the center, concave down and straight to the center, concave up and straight to the center, and then concave up straight to the center. Let's draw that last one again. So something like this, concave up. Alright, so there goes our sine function. This last portion here has been rebellious. So straight and concave down. Okay, so there you have it. Alright, so that is how you draw transformed trig functions. Thanks so much for taking the time to watch this presentation. Really appreciate it. If you found the contents of this tutorial helpful in your studies of the graphing of trig functions, do give us a thumbs up. Your positive feedback is very valuable to us. Don't forget to subscribe to our channel for updates to other cool tutorials on precalc such as this. If you have any questions or comments or requests for videos, just place it in the comment section below and we'll be glad to respond. If you have and don't forget to visit our website mathgotserved.com. You have tons of educational resources to assist you in mastering your maths classes. Thanks again for watching and have a wonderful day. Goodbye.